facade. When writing conversational English for advanced TTS systems, it is crucial to break away from traditional written prose and embrace the messy, spontaneous nature of human speech. Here are the key conventions to follow. 1. Disfluencies and fillers. Real speech is littered with filler words that help speakers pace their thoughts, use, well and so generously. Example, you look at the old panels and they just weren't built for this. 2. Active listening and back-channeling. The listener shouldn't be silent while the other speaks. Use short interjections to show agreement or surprise. Example, host speaker. It takes about 6 hours to charge. Expert speaker. Right. Host speaker, which is a massive draw on the system. Expert speaker. Oh, absolutely. 3. Interruptions and self-corrections. People often change direction mid-sentence or jump in before the other person finishes. Use em dashes or to indicate this. Never use ellipses. Example. You really have to consider the wiring, or if you just plug in it. Wait, let me tell you. 4. Colloquialisms and casual phrasing. Avoid overly formal or academic language unless explaining a specific technical term, and even then, soften it with casual framing. Example. It's basically a heavyweight champion of to power draw, or your system is just going to pack it in. 5. Pacing and turn taking. No one delivers a perfect, unbroken paragraph. Break up long explanations. If one person is explaining something complex, the other should chime in to clarify or prompt the next thought. Example, expert speaker. The aluminum wire actually expands when it gets hot. Host speaker. So it's physically swelling up inside the wall. Expert speaker, exactly. And then it shrinks when it cools down. 6. Starting sentences with conjunctions. People constantly start sentences with and, but, so, or because in spoken English. Example, because if you think about it, that's a lot of heat, and the plastic just melts. Example, natural notes.
It is basically an everyday magic trick. We all do it, and we completely take it for granted.
Oh, totally.
You walk into a dark room, you flip a piece of cheap plastic on the wall, and instantly, electrons moving at a fraction of the speed of light just flood the space with illumination.
Right.
You plug a cord into a socket, and you expect instant cool air, or like a fully charged electric vehicle a few hours later. We don't even think about the sheer physics happening right behind the drywall.
Well, the underlying expectation is that the municipal grid is just this infinite, bottomless well of power, right? Just waiting right behind the paint, ready to do exactly what you want, the exact millisecond you demand it.
Exactly. But for this deep dive, we are looking at what happens when that magic trick actually starts to buckle under the weight of our own expectations.
And it is buckling.
It really is. So we are unpacking a highly detailed stack of source material today, specifically a comprehensive series of service guides and technical blog posts from Burleson Electric. These were authored by John Constantine back in the spring of 2026. And our mission for this deep dive is to unearth that hidden central nervous system running through your home.
Yeah, it's a great metaphor.
We're going to explore how our modern, completely insatiable demand for power is clashing head-on with aging residential infrastructure. And honestly, exactly what you need to know to safely upgrade the spaces you live in.
What's fascinating here is the temporal disconnect.
Oh, wow.
Because we are currently living in an era defined by app-controlled smart environments, continuous high-efficiency HVAC systems, and these massive electric vehicle batteries just sitting in the driveway.
Like heavy hitters.
Exactly. But so many of us are attempting to plug these decidedly futuristic, power-hungry technologies into infrastructure that was literally engineered for the age of the simple incandescent light bulb, and maybe like a single window AC unit.
Okay, let's unpack this, because when I picture that temporal disconnect, it feels a bit like trying to plug a modern supercomputer into a potato battery.
That is a great visual.
Right. You could technically attach the wires and try to force the connection, but eventually the potato's going to roast.
Yeah, it's going to cook.
The underlying system is fundamentally going to crack under the pressure.
That visual is incredibly accurate, honestly. Before anyone gets into the flashy, satisfying upgrades like seamless smart lighting or new outdoor entertainment setups, we really have to examine the foundation handling that electrical load.
Boring stuff.
The boring but crucial stuff. Because the text points out a serious historical risk here. If you are living in a home built before the 1980s, the guides note there is a very high probability your walls are hiding ungrounded wiring, old knob and tube setups, or aluminum wiring.
Okay, so I see terms like knob and tube thrown around on those home renovation shows all the time.
Right, the flip shows.
Yeah, and it's usually right before the budget totally blows up. But for anyone who doesn't spend their weekends doing electrical teardowns, why are these older systems inherently dangerous today? Are they just out of date, or is there a mechanical flaw?
It really comes down to material science and how electricity physically behaves. Let's look at aluminum wiring for a second.
Okay.
It was incredibly popular in the 1960s and 70s because it was cheap. But when electricity flows through a wire, it encounters resistance, and that resistance generates heat.
Basic physics.
Right. Now, aluminum has a much higher coefficient of thermal expansion than copper,
Okay, meaning what?
meaning every time you turn on a heavy appliance, the aluminum wire heats up and physically expands significantly. And then when you turn it off, it cools and contracts.
Oh, wow. So you have this metal wire constantly swelling and shrinking inside the little screws and connectors holding it in place inside your wall.
Precisely. Decades of that constant expanding and contracting literally wiggles the connections loose.
That sounds bad.
It's very bad. Loose connections create these microscopic air gaps between the wire and the terminal. And electricity, being highly energetic, tries to jump across those tiny air gaps to keep flowing.
Right.
That jumping is called arcing. And arcing generates localized temperatures of several thousand degrees.
Wait, thousands of degrees inside the wall.
Yes. Which very quickly degrades the protective plastic insulation around the wire.
Okay, so now take that fragile, aging, expanding, and contracting system and hit it with the heavy weights of modern energy consumption.
Yeah, it's a recipe for disaster.
The sources explicitly name the culprits, pushing these old wires to the brink. First, you have continuous HVAC usage. If we're talking about regions that get sweltering heat in the summer, like the Texas examples mentioned in our guides, your air conditioning is basically demanding massive voltage nonstop.
Oh yeah, running 24/7.
Right. Then you have high-end appliances. And finally, the absolute undisputed heavyweight champion of power, draw the electric vehicle charger.
The EV charger is just the ultimate residential stress test. The text emphasizes that installing a level 2 EV charger is not a DIY plug-and-play Saturday afternoon project.
Let's establish a baseline there, just to be clear. Level 1 is just taking the cord that came with the car and plugging it into a standard 3-prong wall outlet.
Right.
And that barely gives you a few miles of charge per hour. So a level 2 charger is a completely different beast.
Well, it's night and day. A level 2 charger requires 240 volts, and it draws a massive continuous current for 6 to 10 hours at a time.
Wow.
It requires specialized, dedicated circuitry and a professional load calculation. Putting a level 2 charger on an older home's panel is honestly the equivalent of adding an entire second house's worth of power demand onto your existing system.
Wait, really? An entire second house?
Easily. I mean, for context, homes built decades ago were often outfitted with 60 amp or maybe 100 amp electrical panels because back then people just didn't own that many electrical devices.
They had a fridge and some lamps?
Exactly. Today, integrating an EV charger almost universally forces a complete upgrade to a 200 amp panel equipped with highly stable modern copper wiring. An old 60 amp panel simply cannot physically handle the sustained draw of modern life plus an electric car.
Let me challenge that premise for a second.
Sure.
It's very easy for a service guy to say, hey, upgrade your panel, spend the thousands of dollars.
Yeah.
But mechanically speaking, why can't the existing circuit breakers just do their job?
Right, why not just let it trip?
Isn't that their entire purpose? If I plug in my EV and the AC kicks on and it's suddenly too much power, the breaker just trips, the power cuts off, and I'm perfectly safe. Why is a massive proactive upgrade strictly necessary if I have breakers?
The source takes a very firm mechanical stance on this. Relying on reactive breaker trips is significantly more dangerous than most people realize.
Really?
Yes. To understand why, you have to look at how a standard circuit breaker actually functions. Inside that plastic switch is a small bimetallic strip, 2 different metals fused together.
Okay.
When too much current flows through, the strip heats up. Because the 2 metals expand at different rates, the strip physically bends. When it bends far enough, it triggers a spring mechanism that snaps the circuit open, cutting the power.
So it's literally relying on heat to bend a piece of metal to save your house.
Yes. A breaker is a mechanical safety net. But if your safety net is catching you every single day because you are constantly overloading the system, that bimetallic strip is weakening.
Oh, I see.
The internal springs are degrading. Furthermore, frequent tripping means your system is routinely operating right at the absolute edge of its thermal limit. The wires behind your drywall are getting incredibly hot before that breaker finally decides to snap open.
So it's not a harmless reset?
Not at all. A breaker is the very last line of defense before a fire. It is absolutely not a switch you should be using for daily load management.
Which logically brings us to the next phase of the source material. If a breaker is just an emergency net and we shouldn't rely on it to manage our habits, what happens to the wires in the wall before that breaker finally trips?
Right.
How exactly does a home signal that its electrical capacity is just panting, trying to keep up with the demand?
Well, the symptoms of an overtaxed system usually manifest in ways we tend to brush off as minor annoyances.
Yeah, the text lists a few preliminary warning signs. You've got the frequent breaker trips we just analyzed. Then there's the classic dimming or flickering of lights in the living room the exact moment the refrigerator compressor or the AC kicks on.
Very common.
And my personal favorite, unplugging a vacuum cleaner and noticing the plastic wall outlet literally feels warm to the touch.
Yeah, those are clear indicators of high electrical resistance. Your system is struggling to push the required amperage through deteriorating or undersized pathways.
But then the text highlights a symptom I found completely bizarre.
The fish smell.
Yes, you are walking around your house and you notice an acrid odor. Sometimes it smells like burning plastic, which is intuitive. Sometimes it smells like sulfur. But occasionally you might notice a distinct fishy scent hovering near a wall outlet or a light switch.
The infamous fish smell. If we connect this to the bigger picture of the thermal dynamics happening behind the drywall, that odor is a critical hazard warning.
Why fish, though? That is so oddly specific. I mean, I know burning plastic smells like, well, burning plastic, but a fishy smell sounds organic. Is there a specific chemical in older wire casings that reacts to heat in a weird way?
You hit the nail on the head. It is a chemical reaction. It comes down to the specific composition of the plastics and thermosetting resins used to manufacture electrical wire insulation and the hard plastic bodies of outlet receptacles.
Okay.
When a circuit is severely overloaded and the components overheat, or worse, when they are actively arsing and jumping those microscopic gaps we discussed earlier, it generates extreme localized heat.
Right.
And when those specific synthetic resins reach their melting point, they break down chemically and release off gases. The human olfactory system interprets these specific chemical compounds as a strong, fishy, or sometimes urine-like odor.
Oh, that's wild. So you aren't smelling bad seafood. You are smelling the structural failure of your home's electrical insulation.
Exactly. It is a localized thermal event that is on the absolute verge of igniting the wooden studs behind your drywall.
Okay, let's play this out. I smell fish near a specific lamp in the living room. My absolute first instinct is to just unplug the lamp, stop using that specific outlet, and call it a day. Does that solve the problem?
The source material is adamant on this. Absolutely not.
Really? Not even a temporary fix?
No. Unplugging the device removes the immediate electrical load, yes, but it does absolutely nothing to fix the physical damage that has already occurred inside the wall. The wire insulation has already been carbonized and rendered brittle.
The damage is done.
The metal connections are already compromised. The text emphasizes that ignoring these off-gassing issues or trying to use DIY workarounds leads to catastrophic property damage later. You need an immediate professional assessment to open the wall, inspect the hidden damage, and physically cut out and replace the degraded wiring.
Message received. Do not ignore the wall fish.
Definitely do not ignore the wall fish.
But let's look at the brighter side of the guides. Let's say you've done the right thing. You brought in the professionals, you upgraded your home to a robust 200-amp panel, your wiring is solid modern copper, and all the terrifying thermal hazards are mitigated.
Perfect scenario.
Now you actually get to pursue the upgrades that change how you experience the home. And according to the Burleson Guide, the single most popular modern transformation is the LED lighting upgrade.
Oh, yeah. Once the foundation is secure, switching to LEDs is unequivocally the most effective aesthetic and efficiency upgrade a property owner can execute.
And the benefits listed here go far beyond just buying a new bulb at the hardware store. The guide highlights up to 75% energy savings compared to traditional bulbs.
It's massive.
It is. And let's talk about the HRW for a second. An old incandescent bulb works by forcing electricity through a tiny, fragile tungsten filament until it gets so hot it literally glows with visible light.
Right. It's essentially a tiny space heater that happens to produce light as a byproduct.
Exactly. Something like 90% of the energy is wasted as heat.
Whereas an LED, a light-emitting diode, is a solid-state semiconductor. It passes electrical current through a microchip, which illuminates the tiny light sources with almost zero heat byproduct.
Which means your air conditioning isn't fighting against your lighting fixtures.
Exactly.
Plus, the lifespan difference is staggering. The guide cites 15,000 to over 25,000 hours of life for an LED. That completely crushes the 1,000 to 5,000 hours you might get from a traditional incandescent bulb.
It really does.
We are talking about going a decade without having to drag a ladder into the foyer to change a ceiling light.
And the text also provides a rare, transparent breakdown of the real-world costs for these systemic installations.
Oh yeah, the pricing was interesting.
Small local projects range from $150 to $500. Medium upgrades, like outfitting a master suite and kitchen with recessed fixtures, run between $500 and $2,000. And comprehensive large-scale home or commercial jobs like warehouse high-bay lighting or outfitting an entire exterior landscape, those start at $2,000 and scale up. And they note that LEDs are highly durable and perfectly safe for extreme Texas heat outdoors, making them ideal for patio and motion sensor security lighting.
Here's where it gets really interesting, though.
Okay.
Because I caught what looked like a blatant contradiction in the guide, and I want to see if we can deduce what's actually going on.
All right, lay it on me.
If LED lights use 75% less power than the old incandescent bulbs, why does the guide explicitly state that installing large LED smart lighting systems might actually require an electrical panel upgrade? I mean, if the new lights use a fraction of the power, shouldn't my old, weak panel have an even easier time handling them?
It is a fantastic paradox to point out. It seems completely counterintuitive, but the text clarifies that the strain of smart LEDs isn't about the sheer volume of raw power being drawn. It's about the extreme complexity of the delivery and the constant microscopic demands of the control systems.
Are we talking about the actual smart components, like the Wi-Fi chips inside the switches?
Precisely. When you install a comprehensive smart LED system, you aren't just sending power to a dumb wire anymore. You are integrating app-controlled hubs, smart switches, and continuous microloads.
Continuous?
Yeah, every single smart switch in your house requires a constant 247 trickle of power to keep its internal Wi-Fi or Zigbee radio broadcasting so it can listen for commands from your phone.
Ah, so while the light itself draws less power when it's on, the infrastructure commanding the light never actually goes to sleep.
Exactly.
It's a parasitic drain.
Furthermore, older panels and older wiring systems were designed to deliver brute force alternating current. But LEDs run on direct current. They have tiny internal drivers that convert the power. If you try to use older dimmer switches with modern LEDs, it's a disaster.
Why is that?
Well, old dimmers work by rapidly chopping up the alternating current wave, literally turning the power on and off 120 times a second to simulate dimming.
Which an incandescent filament handles fine because it stays hot and glowing during those microsecond power cuts.
Right.
But an LED reacts instantly, which is why putting an LED on an old dimmer makes it flicker erratically or hum loudly.
Exactly. Modernizing a home's lighting requires specialized dimmer switches, neutral wires in every switch box to power those continuous microloads, and a panel capable of delivering a highly stable, clean power profile without voltage drops. It's a shift from delivering raw capacity to delivering precision control.
That makes perfect sense.
Uh-huh.
So we've got the inside of the house beautifully dialed in, the panel is robust, the walls aren't slowly carbonizing, the smart LEDs are humming along with precision control.
All good things.
But none of that precision matters if the umbilical cord connecting your house to the municipal power plant is vulnerable to a stiff breeze.
Oh, absolutely. You can build a masterpiece of engineering inside, but if the main power line is exposed to the elements, your high-tech lifestyle is completely at the mercy of the weather.
Which leads into the final section of our sources, Fortifying the Castle. The guide introduces a major residential trend, moving away from traditional overhead utility poles and toward burying the power lines underground.
They refer to this process as hidden power, and it's a massive shift in how we secure residential infrastructure.
How does it work?
The mechanical process involves precision trenching, digging a deep channel from the street's utility box directly to your home's electrical panel, and then laying heavy-duty PVC conduit to physically house the transmission lines.
If I think about my own neighborhood, whenever there's a severe storm, everyone is staring out their windows at those thick black cables swaying dangerously in the wind, just waiting for a saturated oak branch to come crashing down.
It's so stressful.
Burying the lines removes that anxiety entirely.
Yes. That physical barrier of PVC and compacted earth completely shields the sensitive transmission wires from high-velocity winds, heavy ice accumulation, falling timber, and even burrowing wildlife.
Wow, even wildlife.
Yeah. The text notes that properties with underground utility connections experience a drastic reduction in grid loss outages. And an outage isn't just about missing your favorite show in a dark room. Prolonged outages threaten food security in your refrigerator, they disable critical medical devices, and completely disrupt the ability to work from home.
And let's not ignore the massive aesthetic and financial bonus here. The text points out that physically removing those ugly black utility cables from your sight line instantly elevates the curb appeal of the property.
Oh, for sure.
You get an unobstructed, clean skyline above your yard, which genuinely translates to a boost in property value.
It's a permanent structural upgrade to the resilience of the home. But burying the lines is only the first half of fortifying the property. You've protected the physical wires from external trauma, but you still need a defense mechanism against invisible electrical trauma traveling through the municipal grid itself.
We are talking about surge protection.
Yes.
But I assume the guide isn't talking about the $15 plastic strip from the grocery store that I plug my television into.
Not quite. The source strongly advocates for whole home surge protection, physically hardwired directly into the main breaker box.
How does that actually work mechanically?
Mhm.
I think people imagine a surge protector as some kind of magical force field that bounces lightning away, but obviously it's just physics. If a massive voltage spike hits the house, where does all that energy go?
The best way to visualize a whole home surge protector is not as a shield, but as an electrical pressure relief valve.
Okay, a relief valve.
The utility grid is surprisingly unstable. You have constant microfluctuations, power spikes from the municipal grid redirecting loads, and of course the massive catastrophic voltage spikes caused by nearby lightning strikes.
So a wave of massive electrical pressure comes racing down the line toward your home.
Under normal conditions, the surge protector just sits there passively, but the instant it senses a voltage spike exceeding safe limits, the internal components react in a fraction of a millisecond.
That fast.
Milliseconds. It instantly opens a trap door, a path of least resistance, and shunts that excess dangerous electrical pressure directly into the earth via your home's grounding wire.
Wow.
It dumps the pressure outside before it can ever enter the home's circuits and blow out the delicate, expensive microchips inside your HVAC system, your smart fridge, or your electric vehicle.
Kind of like a medieval moat protecting the castle, combined with a final shield against the grid.
Exactly.
It is incredibly humbling when you realize just how many sophisticated layers of thermal management, chemical science, and pressure relief are required just to maintain that simple magic trick we talked about at the very beginning.
It is a highly orchestrated, incredibly delicate system masquerading as a simple switch.
So, to summarize our journey through this Burleson Electrician Guide, we've explored how the way you illuminate and power your home dictates entirely how it functions, how it feels, and how safe you are. But none of those modern, futuristic conveniences, the electric vehicles, the continuous climate control, the smart LEDs, none of it works without fundamentally respecting the invisible network of circuits hidden behind your drywall.
You simply cannot build a 21st century lifestyle on a 20th century foundation and expect the walls to hold.
So what does this all mean for you listening right now? It means paying close attention to your daily environment. Do not ignore the subtle warning signs your house is giving you.
Right.
If your lights dim every time the AC kicks on, or if you happen to catch a faint organic fish smell near an outlet, do not just unplug the lamp and assume you fixed it. The damage inside the wall is already happening. Value proactive systemic maintenance over dangerous reactive repairs. Your home is desperately trying to tell you what it needs.
This raises an important question, though, and it's something that has been lingering for me as we analyze these escalating power demands.
Oh, let's hear it.
As we continue to integrate incredibly heavy, energy-dense technology into our residences, Level 2 EV chargers, continuous smart systems, advanced climate control, are we approaching an inflection point where a simple connection to a municipal power grid will no longer be sufficient?
That's a scary thought.
Will the modern home eventually need to evolve from being a mere passive consumer of electricity into its own independent, self-contained micropower plant, generating and storing its own energy locally just to keep up with its own insatiable demands?
Wow. Going from flipping a plastic switch to running a personal microplant, the underlying magic trick is getting a whole lot more complicated.
It really is.
It's definitely something to ponder the next time you walk into a dark room and reach for the wall.